Hello, contour integration. This is totally unplanned, and I'm going to try to put a link on the description because I was doing an integral for further mathematicians that involved this particular integral. I thought to myself, as I was doing it, I'm going to do the same thing with complex integration, and I'm going to add it to one of my books eventually. So at the moment, it's not even in one of my books on residue calculus. So this is now our target, is to get in general form this particular integral. There's some particulars here just to make life easier. A is positive. The reason being is I'm trying to, because of course it can be negative, it's just that the two cases have to be done separately. But keeping the A positive, I'm going to integrate on the top half of the plane. And this particular one, in order to do by complex integration, I want to make sure it's the discriminant is negative. So the additional condition we got, b squared minus 4ac for the discriminant of this quadratic, which of course we can write as a little triangle, is negative. So these are the two conditions that we're going to apply, and we're going to use contour integration for something like this. This is fairly standard contour, so we're going to consider, of course, the integral of the same complex function but in z, so 1 over a z squared plus bz plus c 1 over a contour gamma, and perhaps we can guess what this contour will be. It will be, of course, a semicircle on the top half of the complex plane. The real integral will come when we let r standard stuff go to infinity, and we're going to show that the contribution of the semicircular arc goes to 0. All very, very standard stuff. Do we need to, and that's why I put the a's being bigger than 0, because if a is less than 0, I have to use the same contour but upside down and then combine results. Of course, it's just exactly the same thing. So let me just do the drawing that is required for this. So this is now the standard contour that is required for this particular type of integral. No indentations are needed or anything like that, because of course this particular one has the origin is all good as per, because sometimes we have to kind of put a little semicircle there. This is now real z, this is going to be im z, and this is of course a minus r to r. Our gamma is like this, and is traced, of course, in an anti-clockwise direction. Okay, what's the next step? Of course, we're going to use the residue theorem. So this particular integral integrated over gamma, and let's call this little thing little gamma. That's the semicircular arc. It's going to be 2 pi I times the sum of the residues of f of z, that's my f of z here, which lie inside my contour back there. So let's find the poles. It's a quadratic. It will have, because it has a negative discriminant, it's going to have complex answers. So let's solve this particular equation. So if we solve it, I'm going to use a quadratic formula, of course. So z is equal to, and we're going to have, of course, minus b plus or minus the square root of b squared minus 4ac, the whole thing over 2a. And of course, kind of silly now, because of course this bit here is definitely negative, so we can actually say that is going to be minus b there, plus or minus, I'm going to write it as the square root of 4ac, so that will make it now positive when I flip it, and then it will generate, of course, an I over 2a, and for simplicity I'm going to call this the negative of the discriminant because it's easier, so I don't have to keep writing all of this. So it's going to be minus b plus or minus the square root of the negative of the discriminant, lots of I, the whole thing over 2a. So the question is now, where are these two poles in my picture? Are they both inside my my contour? Are they both outside, or is it one inside and one outside? If you look carefully, okay, because this particular equation, just one, sorry, this in complex, it has real coefficients, okay? These particular two answers are of course conjugates, and conjugates, it means basically one is going to be on the top half of the complex plane up here somewhere, and the other one at the bottom. So it's clearly one will be inside. Why is it? How do I know it's not in there? Well, if it's in there, all I'm going to do is I'm going to make my R large enough, sufficiently large, in order to contain it. So this is what I'm planning to do in there. So I'm going to put it without loss of generality here. So this is my pole, and of course there's going to be a conjugate somewhere here. It doesn't really matter. How do I know it's on this side or this side? I don't. It's the simple answer. It could be on either side. It doesn't really matter. And it's going to have, of course, it's the one that has the plus version of the square root. So my pole is at z0. I'm going to identify it as z0 so I don't have to write all of this mess. Z0 is minus b plus the square root, so it has a positive imaginary part, lots of I over 2a. And perhaps I need to write that somewhere. Let me write it here, because I might need it later on, and I need to have it for reference. So minus b plus the square root of the negative of the discriminant, lots of I, the whole thing over 2a. So I hope we're all happy. This is our z0 up here, and it's inside my big gamma. So the next thing, of course, is to find the residue of this particular pole. So standard technique for this, it's a simple pole. So that's the limit as z tends, that's why I label it z0, because I don't want to write all of this down, as z tends to z0. And it's of course z minus z0 times my f of z, which of course is going to be 1 over this. Let me just write it and I'll do on the next line, times f of z, which is of course the limit as z tends to z0. And I can put z minus z0 on the numerator, and on the denominator I've got a z squared plus bz plus c. I can factorize this and cancel the z minus z0, but of course this is a 0 over 0 limit, so probably by L'Hopital's rule, I'm not writing it down, I'm just going to actually do it. So I'm using L'Hopital's from there to there. So this is equal to the limit as z tends to z0, and if I differentiate top and bottom with respect to z, I'm going to get, of course, 1, and I'm going to get 2az plus b. And now I need to take the limit, so that's going to be equal to 1 over 2az0, 2az0 plus b. I don't like the one on the side there, 1 over. Okay, I think I can simplify this. I'm not going to leave it like this. I got my z0 here, so this will actually simplify, I think, if we write it in full. We got 2a times all of this, so it's going to be minus b plus the square root of the negative of the discriminant, lots of I, over 2a. So it's my 2az0, and don't forget we've got a plus b. And of course I'm going to wrap this one because I don't like it on the side. I think lots of things cancel, because of course we got the 2a's that will cancel, and that will leave me a minus b now plus that lots of I plus a b, so the b's will cancel afterwards. So in fact the residue of z0 at z0 is of this pole is 1 over the negative of the discriminant, lots of I. So I'm going to make some room on this side of the board and write what I would normally be writing. At this stage I would have said, okay, therefore the integral around gamma is 2 pi I times this, and I'm going to write it afterwards as two separate integrals. The integral from minus r to r plus the integral around little gamma is of course exactly the same quantity, and then I'm going to show this bit here goes away. So let's write it here, or this line, and I'm going to write the residue there as well. So I'm going to say minus r 2r plus the integral around little gamma, curly bracket, my f of z dz is of course equal to 2 pi I times the only residue, which is of course, I'm going to write on the denominator, probably save a bit of space. 2 pi I times that is the same as of course 2 pi I over the negative of the discriminant, lots of I, and I'm going to be a bit sloppy and just lose these bits here. Okay, and I hope, in fact, if this goes to infinity and vanishes, and this will go minus infinity to infinity, this will be my answer for this particular integral. So all is left for me to do is to actually show the contribution around little gamma is of course 0 in the limiting case. Do I need this? No, I don't. Do I need the residue there? Not the residue, the pole. No, I can rub it off. So let's clear the board, and we got a standard estimation which I've done several times. I'll try to speed through it, and I hope you remember stuff. I'll make some references of course, but not as many as I have done in previous lectures. So I'm going to concentrate on this integral around little gamma. So the modulus around little gamma of f of z dz. We should all be getting a lot better now with these kind of estimations. Of course, around gamma of r, z is of course radius r, standard parameterization, r e to the I theta, dz is of course I r e to the I theta d theta, and my theta will run from 0 to pi, so 0 to pi. Okay, so that's my parameterization. So this is equal to modulus 0 to pi. I cannot use of course Jordan's lemma here because of course I don't have the exponential on the top, but the standard estimation stuff is all good. So it's a little bit messy, this one. I just realized, oh my god, not hard, just messy, and not Lionel Messi, just Messi. Okay, so we're going to have a, right, the z squared is going to be r squared e to the 2I theta. So that's the az squared plus b r e to the I theta plus the c. I got 1 there, and my dz I'm going to write on the top of the fraction, so it's going to be I r e to the I theta. And let's put the d theta in here. Standard line after that, the modulus of a definite integral is less or equal to the definite integral of the modulus of its argument of its integrand. So it's going to look on the next line with this inequality, of course, ar squared e to the 2I theta plus b r e to the I theta plus c I r e to the I theta, and then d theta. And of course nothing cancels here. We're just gonna have to estimate a lot, so let me just use the red pen there. So after that, rules of moduli, the modulus of a fraction, we can move the mods now to individually to the top and to the bottom. So I'm not rewriting that, I'm just merely putting the moduli signs in the appropriate places. Then if we have the product of lots of things, so let me just write it, my tongue is getting twisted and stuck. The mod of z times w could be real or complex, is of course mod z times mod w. So I'm going to apply this on the top. Again, I'm not showing, don't have room to actually write it. So that's modulus of that times modulus of that times modulus of that. I cannot do it here, although I could do it individually here if that wasn't there. Because of the plus is there, I cannot do that. So next thing on the top, the modulus of I is of course 1, And e to the I real, we have said several times, has modulus 1. And if you look in one of the previous lectures, or you can check it yourself, is of course another 1. So the only thing that survives on the top is of course the mod of r. And the mod of r, of course, a positive quantity, is going to be equal to just simply r. What happens now with this line on the denominator? We're going to use the inequality mod of z plus w is greater or equal to the mod of z minus the mod of w, and this is bigger than 0. If it's not bigger than 0, because you might say, how do you know when I subtract this moduli you're going to be bigger than 0? Well, I can say to you, well, if they're not, just swap them around. And it doesn't matter, it's symmetrical, w plus z, and then the w goes there, and the z goes there, and now this becomes greater than 0. And of course, I want to use this in this as a reciprocal. Again, this is very, very standard. The reason I'm writing it is because this is very, very important. So it's going to become that. Okay, so the inequality holds because now both of these are positive quantities. And of course here we have 3, so it doesn't really matter. And in fact the plus and the minuses, it will hardly matter. So it's 3 things here. So I can actually say, well, that's the modulus of a r squared e to the 2I theta minus the modulus of b r. So that's not equal, I beg your pardon, I made a mistake in there. I'm going to correct it in a second. Let me just write that because I'm doing too many things at once. Okay, and of course I got the d theta here. Here, what I've done from this line to this line, of course, these are equal because that's 1, and the r is r. But I'm applying the inequality that I've written up there for 3 as 1 over, and therefore there's another less or equal here from this line to this line, just to be perfectly correct. What is that? I don't even, what is that? Oh, that's a C, a very bad C. It looks like that. Okay, let me just write a little bit better. So that's minus that. Okay, so now, shall we make some room up here? This is very, very standard estimations, very tedious, kind of difficult and intimidating the first time you do them. After that, they're just tedious routine. So I'm going to put there less or equal purely because there were less or equal things along the way. So it's going to be 0 to pi. And now, again, the individual moduli now can be applied because now we got product. So that becomes the modulus of a, which is just a, the modulus of r squared, which is just simply r squared, and the modulus of e to the 2I theta is I real, so it's going to be 1. Once I do, of course, this kind of thing, that's a 1. And then I'm going to have a minus b, and the modulus of r is just r, and the modulus of e to the I theta again is 1, and I'm not going to write it. And then a minus c. It will hardly matter if it was pluses there, I suppose, because of course in the limiting case this will still go to 0, so we can be a bit sloppy. Sometimes I am sloppy with this kind of stuff. I do apologize, I'm not a purist, so sometimes I do things not in an unorthodox manner. So this is now, it has no theta dependence. Pull it outside your integral. A r squared minus br plus minus, doesn't really matter, minus c, 1 d theta, 0 to pi. And I don't want to be rewriting this again. This, of course, will integrate to just pi. So I lost the integral along the way. And this, of course, is of the order. The dominant term on the denominator, if we go to infinity, of course, is the r squared. And the dominant term on the top is just the r, of course. So it's of the order r over r squared is of the order 1 over r, which, of course, goes to 0 as r tends to infinity. And therefore, what I've concluded in this particular line is, as I was expecting, as I mentioned earlier on, the contribution of this as r tends to infinity is in fact 0. And my result follows because, of course, it's just merely writing my answer. It's hardly worth rubbing off the board just to write this, but let's do it. So all I'm left with now, because I even simplified this line there, and in the limiting case now, as r tends to infinity, this vanished as we said. This circle has been blown up to infinity, so that goes minus infinity to infinity. So we got minus infinity to infinity of 1 over, along of course this on the x-axis, my z is just simply x. And I did have mentioned in the past, obviously, the fact x e to the 0i. There's no fractional powers or log, so you can just say there, well, it's just z is x, and my dz is, of course, dx. So it's going to be ax squared plus bx plus c dx is, of course, equal to 2 pi over the square root of the negative of the discriminant. And of course we wanted to put it back into a's, b's and c's, so that's going to be 2 pi. The discriminant, of course, is b squared minus 4ac, but the negative of it will be, of course, 4ac minus b squared. And I must remember to put the link of the lecture that I've done for the further mathematicians. Of course, I didn't use complex integration for this. I've done it by standard A-level techniques. I believe we got exactly the same answer, so you can compare and contrast. I hope you enjoyed it. I hope you find it educational. I hope you understand contour integration now. I have put several lectures now, so join me again very, very soon. Who's laughing now?